Most volcanic islands begin as an eruption of molten rock on the ocean floor. Geologists look for a mantle plume, hot rock rising through the interior. This pushes the crust upward, creating an island and seafloor swell. Over millions of years, the plate moves away. Cut off from the heat, volcanic activity stops and the rock cools. These islands eventually reach a static state. Without the constant addition of new material or the upward pressure of the plume, the volcanic engine is effectively dead. Under this standard model, the cooling seafloor should lose its buoyancy. As the swell deflates, the island is supposed to sink, eventually disappearing beneath the ocean surface. But in the western Atlantic, Bermuda breaks this rule. Its volcanoes have been extinct for 30 million years. There is no active growth occurring, yet the island remains high above the sea level. This chart compares Bermuda to other islands of the same age. It sits on a swell that is roughly 1,600 feet higher than the surrounding ocean floor, an elevation that defies the standard math of island sinking. There is no active mantle plume beneath this part of the Atlantic to explain that height. Bermuda is isolated from the typical heat sources that maintain these seafloor swells. For decades, geologists couldn't reconcile Bermuda's elevation with the known laws of ocean crust cooling. The numbers simply didn't add up. Understanding why Bermuda is still afloat required a closer look at the hidden architecture 20 miles beneath the island. Seismologist William Fraser and Jeffrey Park set out to map the density of the material directly beneath the island to see what was providing its support. They used seismic waves from earthquakes around the globe. As these travel through the interior, they act like an ultrasound for the planet. The waves change speed depending on the rock's density, letting researchers map the subterranean structures. The data showed that Bermuda wasn't being pushed up by a deep mantle plume. Instead, the source of its elevation was much closer to the surface. They found a massive structure embedded within the crust itself that was providing the necessary lift. The scans revealed a 12-mile thick layer of rock just beneath the oceanic crust. Because this lighter, less dense rock is unusually buoyant, it acts like a raft, holding the island and seafloor 1,600 feet higher than normal. In places like Hawaii, heat provides the lift, but in Bermuda, the island stays elevated because of this internal passive buoyancy. This layer, called an underplating, formed tens of millions of years ago when carbon-rich molten rock from the mantle intruded into the base of the crust and cooled in place. This material likely originated deep in the Earth hundreds of millions of years ago, potentially dating back to the formation of the supercontinent Pangaea. It remained trapped in the mantle until Bermuda's period of volcanic activity pulled it into the base of the crust. Today, Bermuda is held up by this ancient rock raft, a 12-mile thick foundation forged long before the island ever reached the surface. The discovery of this underplating proves that the standard model of how islands rise and fall is incomplete. Researchers are now looking for similar structures beneath other islands to determine if these buoyant rock rafts are a widespread geological feature. This find suggests there are convective processes within the mantle that we don't yet fully understand, as material is reaching the crust in ways that don't involve a classic mantle plume. It shows that even without active volcanoes, the land we stand on can be supported by thick, buoyant rock hidden deep